We're going to take a look at something called implicit differentiation. Now, the good news here is none of our rules for taking derivatives are going to change. This is really just looking at the derivative in a new light, or in a different situation, really. Up until this point, we have taken derivatives what's called explicit differentiation. What explicit means is we were able to directly say what the function of y was, right? We could say y is strictly a function of x. So over here, this was our function of x. But what if the x's and y's are all mixed together and there's no way to get y alone? Like if we had x squared y to the fifth minus e to the y plus 2y equals 0. Okay, so here again, just like this, we have an equation involving x's and y's, but in this case, there's no way to actually solve for y. Now, since we can't solve for y, does that mean that we're unable to figure out what y prime equals, or dy dx, whichever notation you want to use? Well, the answer is we actually can. And we already know how to do this from like one of our basic rules. Think back to like day one derivatives. We learned our power rule. We said the derivative with respect to x of x to the n was bring down the power, take one away from the power. Because we knew that the x, when we're taking a derivative with respect to x, and there was our x. Then we learned about the chain rule and we expanded this. And we said if it's u to the n, the derivative would be n u to the n minus 1. But then we got to take the derivative of the inside, so we multiplied by u prime. Now here we were saying u was some function of x, but we didn't know what it was. But we did know we had to multiply by the derivative of that. Well, the same thing's going to apply here. Here we're going to assume y is some function of x. Like if we could solve for it, we would say y is some function of x, but we can't. But we know it kind of could be, which means anytime we take the derivative of a y, a function of x, we're going to have to multiply by y prime, or dy dx. All right, so it's not as bad as it sounds. Like I said, our rules are just going to come into play. So let's start out with a very straightforward expression. Let's say we have x squared plus y squared equal to 4. And our directions here are find y prime. Now in this one, we could actually solve for y, right? We could move the x squared over, take the square root. We would get a plus or minus, but technically we could do it. But here it's actually easier just to take the derivative of this sentence. Now since we're looking for y prime, or remember that's the derivative of y with respect to x. When I take the derivative of this with respect to x, since this is just a function of x, the derivative of that would be 2x plus the derivative of this. Now we take the derivative exactly like we would like if it was an x, so the derivative of y squared is 2y. But since we're assuming y is a function of x, we have to use our chain rule and multiply by y prime. And of course on the other side, the derivative of 4 is 0. Right. After this step, after you've taken the derivative, now you have a little bit of algebra to do. You need to solve for y prime. Now the good news is it's always a linear equation with respect to y prime, which means get all your stuff that has y prime on one side, everything that doesn't have a y prime on the other side. Sometimes you need to factor out the y prime and then divide. So let's see. We already have all of our y primes on the left, so let's move everything that doesn't have a y prime over there to the right. And then divide everything that's not a y prime. So we get y primes equal to x over y. Okay, so here's our derivative. Now this is slightly different from what we've seen in the past, because now notice our derivative doesn't just have x's in it, it has x's and y's. But this still tells us about the slope of the tangent line of our original function at any given spot. The only difference is now you'd have to plug in what? An x value and a y value, so you have to plug in the complete point. All right, let's just try a couple more of these, because again, it's not too bad. Let's say we have 4x squared y cubed plus 2x squared minus 3y is equal to 4. And again, our directions are going to be the same. I'm just going to leave them right here. Find y prime or dy dx. I think I'm going to use dy dx this time just so we can use the notation. Now remember, the whole idea for this is anytime we have to take the derivative of a y, a function of y, we have to multiply by y prime. Now let's start with this first term. Since we have x's and y's multiplied together, we need to do our product rule. Now, if you're to the point to where you can do this in your head, that's fine. But I'm going to go over here to the side and do a little bit. Here we're going to say u is equal to 4x squared, v is equal to y cubed. So u prime is 8x, v prime will be 3y squared. But since we took the derivative of a y, we also get a y prime. All right, so for our product rule, remember it is u prime v plus v prime u. So u prime, that's going to be 8x times v, y cubed, plus v prime times u. So let's see, 3 times 4 is going to be 12x squared y prime. Okay, so that's the derivative of our first term. As we move across here, the derivative of 2x squared will just be 4x. Minus the derivative of 3y, well, that'd just be negative 3, but then we got to multiply by the y prime, and the derivative of 4 is 0. Okay, so for the first term we had to do the product rule, but for each of the ones down there was just the power rule. And remember, anytime you take the derivative of y, you get a y prime. All right, now it's just algebra. So we're going to get everything that has a y prime on one side, everything that doesn't have a y prime to the other side, and then divide basically. So all of our y primes are already on the left. So let's get everything that doesn't have a y prime to the right. So I'll do this in 2 steps. You can do it in 1. Ooh, that's a 3. Okay, so what do we have? We have 12x squared y prime plus 4x minus 3y prime is equal to negative 8xy cubed. Now let's move our 4x to the other side. So 12x squared y prime minus 3y prime is equal to negative xy cubed minus 4x. Okay, so we got everything that's got a y prime on one side, everything that doesn't have a y prime on the other side. Now, since we have more than one thing that has a y prime, like over here we only had one, but over here we have more than one, you need to factor out the y prime. And we get 12x squared y squared minus 3, negative 8xy cubed minus 4x. So now we can see exactly what's in front of the y prime. Let's get our scratch work out of the way. So what I'll bring this up over here. So we have y prime 12x squared y squared minus 3 is equal to negative 8xy cubed minus 4x. So all we got to do is divide both sides by whatever's in front of our y prime. Divide by 12x squared y squared minus 3. So there's our derivative. Y prime is negative 8xy cubed minus 4x. 12x squared y squared minus 3. Okay, so there is our derivative. We took it implicitly. Now again, notice the derivative has x's and y's in it. So if you wanted to know the slope of the tangent line at some point on the original graph, on this thing, then you'd have to plug in an x and a y value to find the slope of that tangent line. All right, so you notice we're still using the exact same rules for taking derivatives that we always have been, except for now, anytime we take the derivative of y, we need to multiply by y prime. Let's try one more here, maybe a little uglier. Let's say we had y squared is equal to the natural log of x cubed plus y to the 4th. All right, pretty ugly looking. So this one's going to be the hardest one yet. So if you'd like, hit pause real quick, give it a shot. It's not going to be easy, but give it a shot and see how you do. All right, if you're back, let's see. We were told to find our derivative. Well, I said I was going to use dy dx on that last one. I lied. I'll use it on this one. All right, so we're told to find y prime or dy dx. So the derivative of y squared is 2y. But then we got to multiply by the derivative inside, so we multiply by our y prime or dy dx. On the right-hand side, let's see, we have the derivative of the natural log. We know the derivative of the natural log is 1 over the argument times the derivative of this argument. So what is the derivative of x cubed plus y to the 4th? Well, the derivative of x cubed is just 3x squared. The derivative of y to the 4th will be 4y cubed. We multiplied by we took the derivative of y, so that'll be dy dx. All right, so let's go ahead on the right-hand side and let's distribute, because again, this is going to be pretty ugly. When I distribute this, I get 3x squared over x cubed plus y to the fourth plus 4y cubed dy dx over x cubed plus y to the fourth. Okay, so what do we want to do? We want to get all of our dy dx's on one side and everything that doesn't have a dy dx the other. So I'm going to go ahead and move all of this over here. So I'm going to subtract this. I'm going to write this as 4y cubed. And I'm going to write this just a little bit different to make it a little bit easier to read. Oh, let's see. So this is going to be y to the fourth dy dx. And if I subtract that from this side, I get negative 4y to the third x cubed plus y to the fourth dy dx. So on the left-hand side, it's ugly, but what do we have? We have 2y dy dx minus 4y cubed over x cubed plus y to the fourth dy dx is equal to 3x squared over x cubed plus y to the fourth. All right, still kind of messy looking, but we really didn't do anything but just simple algebra, right? We moved everything that had the dy dx to one side, everything that doesn't on the other side. Now we're going to factor out a dy dx. I'll use some big brackets here. So we have 2y minus 4y to the third, x cubed plus y to the fourth, three x squared over x cubed plus y to the fourth. So now what we got to do is divide both sides by all this mess. Now I'm not going to write this out, it's just we're divide that side, and we're still going to have to do some algebra here. So I'm going to divide both sides by this. On this side it goes away. On this side I get 3x squared, x cubed plus y to the fourth, all over 2y minus 4y cubed over x cubed plus y to the fourth. Now, technically, that horribleness is our answer, but it's not simplified. So if this was a problem in a textbook, this is not how you'd see your answer. Now, the easiest way to deal with this is a complex fraction, right? We have one big fraction with smaller fractions in it. We want to clear the smaller fraction, so I'm going to multiply the top and the bottom of the big fraction by our least common denominator. So our common, what denominators do we have? We have x cubed plus y to the fourth, x cubed plus y to the fourth, and the denominator here is a 1. So our least common denominator would be x cubed plus y to the fourth. All right, I'm going to do this in just a couple of steps. On the top, let's see, I'll write this out one more time. Now, since we only have one term on the top, that's going to be 3x squared, x cubed plus y to the fourth times x cubed plus y to the fourth. On the bottom, we have two terms inside here, so we need to distribute. So that's 2y times x cubed y to the fourth minus our 4y cubed over x cubed plus y to the fourth times x cubed plus y to the fourth. All right, it looks messier, but it's going to turn out to be really nice here at the next step. Now, the reason we did this, multiply the top and the bottom by our least common denominator, that should get rid of the smaller fractions. Notice on the top, that's going to reduce with that. So we have dy dx is equal to just 3x squared on the top. Now on the bottom here, this is all multiplication, so we're not going to cancel this, so it's going to be what? 2x cubed y plus 2y to the fifth. And let's see, over here, again, the reason we did this is now this will cancel with that, and we have 4y to the third. So minus 4y to the third. Okay, so if you notice, that looks much, much nicer than what we could have ended up over here. Like always, algebra is going to come into play when you're doing these implicit derivatives. So now notice, remember, this is the equation of the tangent line to our original function. So all you'd have to do is plug in whatever point you wanted to know the slope at. So you plug in an x value and a y value, and that would give you the slope of the tangent line of the curve that we were originally given. So implicit differentiation, all our rules are exactly the same for taking derivatives. It's got to remember, anytime you take the derivative of a function of y, like here, when we did the derivative of y to the fourth, you get a y prime or dy dx, whichever notation that you're using.